Hi there. Today we're looking at Gradient Surgery for MultiTask Learning by Tianhe Yu, Saurabh Kumar, Abhishek Gupta, Sergey Levine, Carol Hausman, and Chelsea Finn. So in this paper, the concern is a thing called multitask learning. Now, what is multitask learning? So this has some very subtle distinctions from other things. That's, I think, why it's important to look at it a bit. So let's say you have multiple tasks, a learning problem in multiple tasks. This seems easy enough, right? So what we mean is that we have the same input, but then we want to perform two different tasks. So task 1 and task 2. Sorry, 2. So it could be something like task 1, if the input is a food, right? A food object. The task 1 could it be, is it a fruit? Right? Task 2 could be, how many calories does it have? Right, the input is this food item here, and you want to know both things. Is it a fruit, and how many calories does it have? And ideally, so what you could do is you could train two separate machine learning classifiers, right? Classifier 1 simply does the is it a fruit thing. Task 2 simply does how many calories does it have. Let's actually say this is a food picture. Right, since Instagram is full of food pictures, we have lots of training data, right? At least unsupervised. People usually label it. And we could train two different things, but it would be nice, since they're both kind of dealing with the same input, so they actually deal with the same input distribution. It would be nice if we could kind of share a representation, right? So maybe we have some neural network here with many layers, and then we have, at the end, we take this hidden representation here, and we just have maybe one or two fully connected layers for each individual task. But our goal would be that the hidden representation here is shared. So, shared representation. And why could that help? Because we might have maybe we have lots of training data for the how many calories does it have, right? But we don't have that much training data for is it a fruit. So lots of training data here, big database, but only like a handful of data points for the second task. Or we might just not have much training data at all for both tasks, and we just might benefit from training this shared representation. You might have already seen this with something like BERT. So in BERT's case, the input is text, right? And then you do something different. That's why BERT is different than multitask learning. What you do in BERT is you do this masked language model pre-training. So that's step 1. And then in step 2, you take this and then you fine-tune it on a number of tasks, right? So here, question answering, sentiment detection, entailment, and so on. This is different. This is called pre-training and fine-tuning. In multitask learning, we actually want to train on different tasks at the same time. Maybe they have different data, right? And we simply want to create this shared representation, and we hope that by combining these tasks, we might learn them better than if we were to learn each task individually. All right, so this paper says there's a big problem with things like this, and they illustrate this in this example right here. So let's say you have a multitask objective, and the learning landscape looks like this. So the objective for task 1 is the following. So this you have to have to imagine this is maybe a neural network with just 2 weights, right? Here is weight 1, and here is weight 2. And this is what the optimization landscape looks like for task 1. If you're not used to this kind of depiction, the light parts up here and here are high values for the loss function, and the darker parts are low values for the loss function. So you want to get to the darker parts. Now, usually we discuss things like this in terms of optimization. So, for example, we would talk about SGD, and we would talk about the fact that, oh, if we have too large of a, so if you're here, where does the gradient point? The gradient points towards the direction of steepest increase, so here, so the negative gradient would point down. Now if we have a SGD, maybe we would go here, and then we take another gradient step, we would go here, right? Oh, now we've gone too far, right? So the gradient now points this direction, so we go here, and then we just continue this, right? So this is a problem with SGD, and what we can do is we can decrease the step size, for example, and then we converge in this, or we can use something like Atom that adjusts the gradient to the variance of the gradient landscape, things like this, right? So these are problems in optimization. But what happens when you have a multitask objective is that for just task 1, the optimization landscape would look like this, right? If you were just to train your neural network, if you were to just train this part, and we just look here is like theta 1 and here is theta 2. These are the 2 weights we care about right now. Everything else, let's say, is fixed. Task 1 looks like this. But for task 2, because it's a different task, right, we need to set the weights differently to get our desired output. It looks different. So our loss function is going to be a combination. So our loss function is going to be the loss function for a given sample. It's going to be the loss on task 1 of that sample plus the loss of task 2 on that sample. So that's going to be the combination you see on the right. So this plus this equals this right here. So you can see in task 1, it almost, let's say it didn't matter whether we were here or here. Both had a relatively low loss value, right? But you can see in task 2, this point here is not an optimum. Well, this point, or maybe these are somewhat close together. So if you add them, you can see that now this thing here still has a low value, but not as low as this is much darker, right? So the landscape for both tasks together looks differently from the landscape of either task alone. So your goal is to find this optimal point, an optimal point here that works for both tasks. Now, the paper identifies the paper identifies problems with this multitask learning, and they say the problem is that you can have what are called conflicting gradients. So if you look at where the gradients point in the different tasks. So if we go by task 2, let me put that in again, and we care about the point right here that they care about, right? And they use Atom in this case, and their starting point is right here, and they've come this way so far. So we're going to draw this in here and draw this in right here, and we'll stop a little bit before that valley, right? So let's analyze the gradient. The gradient in task 1 actually points in this direction. You see, down the valley, right? And it's pretty big because it's pretty steep, right? You can see the curves here getting closer and closer together. That means the gradient is pretty steep and it points in that direction. Whereas for task 2, if you're here, right, the gradient actually points in this direction, but not as steep, right? Because here the lines are pretty far apart still. So that means it's relatively flat. This is what the paper calls conflicting gradients, and they're drawn in here. I'm going to draw them just a little bit larger. So these two gradients, first of all, they have different magnitude. You see that the magnitude of this is much larger than the magnitude of this. And also their angle between them is large. That means conflicting, that they're more than 90 degrees apart from each other. And this results, if you calculate the resulting gradient, of course, this results in a gradient like this, right? So our algorithm wouldn't actually go down this valley, it would go up the hill again, because you have differently sized gradients from the different tasks that go in different directions. Now, the important point, I was wondering for a long time, what's the difference between this and simply saying, look, any data set, right, your loss on any data set D is just the sum of the loss of your individual data points xi. Because it is the same case that you can have different data points and the gradients that you get, right? So that would result, if you've never done optimization, I'm sorry, I'm going a bit fast, that would result in the gradient with respect to your weights of your loss over the entire data set is, of course, approximated by the 1 over n in your mini batch. So by the gradients in your mini batch, right? So let's call this the loss of xi. This is completely illegible. But what I'm saying is that your total gradient is the average of your individual data points, and these might be conflicting as well, right? You could have that one points in this direction and the other one points in that direction, and we've done this just and things like Atom and SGD actually are able to handle that just fine because we do this average operation. I think what is different here is in multitask learning is that the tasks distribution is not like stochastically IID, let's say. So in this case, you can always count on that the expectation will average out this noise. So this noise, if you go in expectation, right, if you do mini batches and aggregate over the whole data set, then that will kind of even out, because for the different data points, okay, one gradient might be larger, one might be smaller, but there's no systematic error, or there's no systematic bias that comes from the different data points. Here, you have, as we said, one task might be much harder than the other task, right? Or you might have much more data, or the loss function is just larger, like magnitude-wise. So you can have any number of systematic biases that the different tasks have with each other, and therefore the conflicting gradients seem to be a problem. So this paper does a good job of analyzing the situation of conflicting gradients, and what I find particularly interesting is that they, first of all, they propose an algorithm to deal with these conflicting gradients. So they say whenever two gradients are conflicting, right, what we would do is we would project them on the normal plane of each other, right? So for example, here in step B, we take the gradient of task I and we project it onto the normal plane of gradient from the task J, right? And if we do this, and they have a whole algorithm where it's general, so if we do this for multiple tasks, so basically we get a mini batch of tasks, right? So they generalize this to that you have a bunch of tasks. We get the different gradients, and these can be stochastic because we can do this with stochastic data sets. We go through the batch, and if the gradients are conflicting, we simply project the gradients onto each other. And that will result now in a set of non-conflicting gradients. You might be a bit appalled by this. I was at first when I saw this, but they actually do, as I said, a good job of analyzing this. So they have two theorems here, which I find interesting. So theorem 1 is, assume these are convex and differentiable, so somewhat standard assumptions in optimization. They say then the PCGrad update rule with a step size smaller than 1 over L, L is the Lipschitz constant, will converge either to a location where the cosine is exactly -1 between two gradients. That never happens except if you construct it, or the optimal value, right? So this is basically a consistency theorem saying that this algorithm will still converge to the optimum value. This is the loss. So this loss is the sum of loss 1 and loss 2, right, of these two tasks. So for two tasks, they prove that the algorithm will still go to the correct point if you run it long enough. Doesn't say anything about the speed, though. This is where theorem 2 comes in. Theorem 2 says, suppose L is differentiable and the gradient of L is Lipschitz continuous, blah, blah, this again, same assumptions, except no longer need convexity. Let theta mt, which is the multitask gradient, and theta, sorry, not the gradient, the parameters, theta PCGrad be the parameters after applying one update to theta with G and PCGrad modified G. So this mt is that would be kind of the original algorithm without their method, and this here would be with their method. Moreover, assume a bunch of things, which we'll go into soon. Then the loss function of the PCGrad theta is smaller or equal than the loss function of the MT, of the original. So what does it mean? It means that if you're in your optimization landscape and you're somewhere here, right, and your optimum is somewhere here, and your loss function is kind of how far away are you from this optimum, right? It means that as long as these conditions are given, if you do your update without their method, which would be, so here would be theta mt, or with their method, theta PCGrad, then the loss function that you get from their method will be smaller than the loss function that you get without their method, right? So this is a theorem, they prove it, and for this to be the case, they need these three things. So let's go from the back. The third one is a condition on the loss function, on the step size. And you can say, okay, the step size needs to be large enough. You can set the step size. This here, what is this? This here needs to be this is a condition on this epsilon. So what's this thing? It is a curvature bounding measure, and that is compared to little l, and little l here is this thing. It is a constant that must be smaller than h, and h is up here, is the curvature. So it depends on the curvature, right? It depends on the curvature fulfilling some condition. They state down here, the curvature of the multitask gradient should be large. And the first condition we've already seen is that the cosine of the angles needs to be smaller than negative something that depends on the gradients. And this here turns out actually to be the magnitudes of the gradients. So this here we can neglect. That's a step size condition. This here means the gradients should be conflicting. And this here means that there should be sufficient curvature in the loss function. This is exactly what we saw at the beginning in this thing here. So there was a sufficient curvature because in one direction the gradient was very steep and in the other direction it wasn't, which basically means there is a change of steepness, right? There's a change of steepness in one direction versus the other direction. And also the two gradients were conflicting, which we saw right here. If this is the case, then this algorithm will bring you faster to the optimum than the normal algorithm, but only if this is given. And notably, this can change step to step. They actually call this the holy trifecta, evil trifecta, something. They have a name for it. But I'm going to read you out the conditions that how they describe it. The conditions are, first, the angle between the task gradients is not too small, i.e. the two tasks need to conflict sufficiently. Second, the difference in magnitude needs to be sufficiently large. Third, the curvature of the multitask gradient should be large. And fourth, the learning rate should be big enough such that large curvature would lead to overestimation of performance improvement on the dominating task and underestimation of performance degradation on the dominated task. So here you see a little subtlety. I said before that this condition here was negligible because you can set the task size. In actuality, this you can, so I'm not meaning to rag on this, but what does it mean? The learning rate should be big enough such that blah, blah, blah. And what comes here seems to be negative, right? Such that the large curvature would lead to overestimation, which basically means this method, this thing here, counts if the step size is large. So that means if I were to play devil's advocate, if I have a problem like this, I could either, right? I could either use their method, PCGrad, or I could just decrease my learning rate and use the classic algorithm. Because if I just decrease my learning rate relative to the curvature, then this theorem would no longer hold, and it would no longer be the case that their algorithm gives me a faster convergence. Right? So there's two ways of looking at these things. It's like, yes, in these conditions, this algorithm is better, but it is better because someone has set the learning rate too high, and this algorithm kind of fixes that. Now, the upside to this is, of course, that usually you don't want to kind of set your learning rate in accordance with the curvature of the problem and so on. You don't know the curvature most of the time, so you just set some learning rate. And their algorithm appears to be working also when this learning rate is smaller. It's just not guaranteed to outperform the classic algorithm. But I just find this interesting in terms of how you read a paper, right? If you read a paper, you come across something like this. These conditions, you can always see them as here is what needs to happen for us to succeed, or here is what needs to happen for the others to fail. And therefore, we're the only ones that succeed in this regime. Though, yeah, as I said, it's a cool algorithm, but I found that to be funny. All right, so they test this on MultiTask, which these MT10 and MT50 benchmarks are these robotic manipulations. So MultiTask doesn't only mean like supervised learning. In this case, it's actually multitask reinforcement learning. So here you have everything. You have mini batches, you have episodes, and you have multiple tasks. So this is everything together. Very cool. And you in their actual implementation, they say what they do is they have these multiple tasks. So they have the agent, and they first select a task. So for example here, pull this, right? Then they generate an episode by interacting with the environment, forth and back. Then they put that episode into a replay buffer. Then they maybe select another task and so on, so until they have a bunch of data in their replay buffer from different tasks. Then they sample episodes from different tasks, right? From task 1, task 2, and so on. And that will become a mini batch in the learning procedure. So pretty intricate thing. But of course, the hope is that you can learn kind of a shared representation that you can then perform all of these tasks faster than if you were to learn them each independently. So the MT10 and MT50 come from this, and I think they also have goal condition pushing, where the task is simply to push something to a what they call goal conditioned. And the cool thing about this is it's not only 50 tasks, but you can produce an infinity of tasks, because you can always specify a new location where you should push something to, right? So that's fairly cool. And oh yeah, the curves. So you see that if you do something like soft actor critic or multi-head soft actor critic, so this multi-head soft actor critic is probably the closest to what I defined at the beginning, where you have this shared representation and then the individual heads, and you can see that severely underperforms against the SAC plus PCGrad plus their method. That seems to outperform fairly consistently, even against learning the tasks independently. So it learns much faster than if you were to learn these tasks just independently from each other, which is pretty cool, right? So I think that's pretty cool. All right, so they do actually interesting investigations. First of all, they research, okay, during these learning runs, what is the curvature here? And the curvature of the loss function, they measure like this. So basically all this is a consequence of a Taylor approximation. So if you have like f of x, you can write this as f of some x0 plus the gradient of f plus the gradient of f times x here. Sorry, at x0 times x in this direction. And then if you subtract, so this is a first order approximation to the function on the right. Then if you bring this over here, if you subtract the two sides from each other, then you can see there's the difference between the actual function and the first order approximation of the function. That is most likely the curvature. Now it is not, it is like every higher order term, but the assumption is that the dominant higher order term will be the curvature. Right, so this would be this, except they do it not doing the x and x0, they do it at theta t and theta t plus 1. So you can see this is the first order approximation, and this is the actual function value after they do a step, and the resulting thing will be the curvature, or dominated by the curvature. So they analyze this over the course of learning, and they see that it actually increases as you go on. And just, I'm not a big fan of like just large numbers, but the numbers seem to be large, right? Just compared to what you can handle with a computer, the numbers seem to be large, and they seem to be getting larger in order of magnitude steps across training iterations. So I'm going to believe them that this curvature is given. I would have liked to have it seen compared to just a single task instead of a multitask. Instead of comparing these things, which is useless because they reach different losses, right? So it's pretty useless to compare their curvature across the number of iterations. What I would have liked to see is a comparison multitask versus single task, and to show me that in single task learning this curvature doesn't happen. Here you have the percentage of update steps where conditions A and B are held. You remember condition A was the condition on the conflicting angle. Condition B was the condition that the curvature is large enough. And you can see that as you go on with learning, these dotted and dashed lines, the conditions hold almost entirely at the beginning of learning, but then still hold in a big time of the steps. So here is like about half the steps still at the end of training. These conditions hold. So it is fairly good evidence that often the problems that they say are real are really there, and then therefore their algorithm helps, right? So here's the average, the per task average return. And interestingly, they say in the text, look, this task here seems to be easier, right? And the task 2, which is the dotted line, seems to be harder. So SAC, the baseline algorithm, never really manages to learn task 2, whereas this PCGrad manages after a while to learn it. And at that point, something happens over here, which I'm not super sure. Yeah, that's what they say in the text, but I have to squint a lot to see that exactly at that position something happens. Suffice to say that the PCGrad is able to learn the task that SAC isn't able to learn, because probably task 1 is completely dominating the gradient at that point, right? All right, so this was the paper. I invite you to read it, and thanks for listening. Bye-bye.